x to the 3/5 equals 1,000, then how I probably do this one, trying to get rid of this rational exponent here so I can solve for x, I would take each side and raise it to the reciprocal of that power. Now, as I'm doing that, I see this 1,000 over here. Maybe I might create a smaller base with that 1,000. 1,000, you got multiples of 10 here, so I could say 10 to the third is 1,000, right? Got to raise both sides to that power of 5/3. So if you do that, notice how it works out. When you raise the reciprocal over here, everything's canceling. So that gives you that x to the first you need. Since we already changed the base over here, multiplying power to power, these 3's cancel, leaving you with 10 to the 5th. So you could say that x equals 10 to the 5th, or spell out the zeros. 1, 2, 3, 4, 5. X equals 100,000. All right, on number 10 here, we've got 2/5 equals a quantity of 3y raised to a negative 1/2 power. If I'm solving this one, I'm starting with that negative exponent. I want to create a positive power, so use that reciprocal idea where I bump the 3y down, got my power 1/2 attached. We notice how there's a proportion here. So I could do a little cross multiplying maybe. If you cross multiply, you've got 2 times the quantity of 3y raised to 1/2. That equals 5. And this is one way to do it, right? Now, because I've got this quantity here being raised to that power, and I want to use an approach kind of like I did over there on number 9, where I'm raising each side to the reciprocal idea. So in this case, I'd be raising each side to 2. Might be easier to take this part that's attached, divide it over. So you got 3y to the 1/2 equals 5/2. Now go ahead and square both sides. Right, if I square this side, and if I square this side, we're going to be left with 3y, because we know these 2's are canceling each other. So power left on the quantity is 1. That's going to equal 5/2 squared, which is 25 over 4. Solving for y, if you divide by 3, well, dividing by 3 is the same as multiplying by 1/3. So I take 1/3, I multiply to 25/4. That's 25 over 12. So 11 doesn't differ too much, other than the fact that you've got a binomial expression here being raised to that rational exponent. So it's m minus 17 raised to the 3/4 equal to 64 there. If I go ahead and eliminate that rational exponent, go ahead and raise both sides to the reciprocal, which would be 4/3. Let's see where that would get me. Got this 4 canceling, this 3 canceling, so power would be 1 that's left on the quantity of m minus 17. That equals over here. Let's go ahead and maybe create a common base, or not a common base, sorry, a prime base for 64. That'd be 2 to the 6th, right? So 2 to the 6th would be raised to that 4/3 power. By creating that prime base, well, 2 to the 6th, I'm taking that 6 and raising that to the 4/3, you've got 24 over 3, right? So if I got 24 over 3, this 2 is really being raised to a power of 8. Now, it would probably be helpful to calculate what 2 to the 8th is. What is 2 to the 8th? Check me on that. I believe that's right. 256, okay. If you add 17 now to both sides, you got your answer. So adding 17 over, that's going to be 273. Yeah, I'd say on this one, if this looks like a quadratic, and let's say for a moment here, because I've got some funky looking powers to work with here, let's say for a moment I had a squared plus a minus 20 equals 0, right? Let's say I had that formation instead. That'd be a little less intimidating, right? We'd know what to do. We try to factor this out maybe to solve. So just kind of go with me here for a minute. We factor this out. Got some A's, right? Looks like 5 and 4 would be a good combination to try. Make that a plus 5 and minus 4. Knowing that we're going to set each of these factors equal to 0 to solve, then A would equal negative 5 from the first factor, right? And A would equal 4 from the second. So if that was a quadratic, a squared plus a minus 20 equals 0, given to us in the first place, not a big deal. Right, we can solve that. If we're creative about this, what I would do, go back to the original equation now to try and make sense of this further. Notice if you let, since I used a here, I'll use a again, let a equal x to the 1/3. Wherever I see a's here, if I insert 1/3, or I'm sorry, x to the 1/3, and work it out, it actually takes me back up to here, right? I mean, think about it. If this is x to the 1/3, and you're squaring it, that gives you x to the 2/3, right? And obviously, if this is x to the 1/3, that gives you x to the 1/3 there. It's a creative kind of substitution. So, if I let a equal x to the 1/3, and I find out in the end here, solving this in terms of a, that a is negative 5 and a is 4, then I could say, all right, x to the 1/3 must be negative 5, and x to the 1/3 must be 4. So if we extend this out a little bit further, knowing we're going to use reciprocal powers here to cancel out those rational exponents, I would be cubing both sides here. All right, cube both sides on that equation, cube both sides on this equation. By doing that, x is left. For this equation, you got negative 5 cubed. That's going to be negative 125. That's going to be one solution. And over here for this equation, cube both sides, x is going to equal 4 cubed. So 4 cubed is 64. That'd be another solution for x. All right, so similar scenario here on 13. You got x minus 4x to the 1/2 plus 3 equals 0. Kind of got that quadratic look to it. So I'm going to start on this one by letting a equal. If I go back and look at what happened on this last one, let's see. We let a equal x to the 1/3, and x to the 1/3 happened to be attached to that middle term, right? So let's see if that works out on this one. Let a equal, we'll use x to the 1/2. That's attached to the middle term. All right, so if that's going to be true, to get this x back, knowing that a is x to the 1/2, well, let's see, what's x going to be? I'd have to square both sides, right, to figure out what x is going to be. If I square both sides, what's x going to be? If you square both sides, it's going to be a squared. So we're going to have a squared minus 4 times a, because that represents the x to the 1/2, plus 3 equal to 0. So yeah, if I'm doing this quadratic substitution correctly, it should work out where first term's squared term, right? Second term to the first. And then you got your constant term there, in this case, plus 3. All right, is this factorable? You try to factor it out. Got some A's. Got some 3's and 1's. Make it all negative, right? That should work. So when you take each of these factors, set each of those factors equal to 0 and solve. A minus 3, if that equals 0, then A equals 3. A minus 1, if that equals 0, then A equals 1. We're not solving for A, we're solving for x. So take the A out. Replace it with the x to the 1/2. Got x to the 1/2 equals 3. Got x to the 1/2 equals 1. Using reciprocals here to clear out the powers, that reciprocal of 1/2 would be 2, so we're basically squaring both sides. If we square both sides, we find that x equals 9 here and x equals 1 here. As it stands on 14, since we have an issue here where x's are located up in the exponent, we've got 81 raised to a 2x minus 3 equal to 27 raised to a 7 minus x. We need to get those x's down the same level to play with. So since 81 and 27 share some prime bases here we can use, that prime base being 3, I'm going to write 81 as 3 to the 4th. That's being raised to that 2x minus 3. Rewrite 27 as 3 to the 3rd. Raise that to 7 minus x. Using the power-to-power idea, I'm going to take this 4, distribute through to 2x minus 3. You got 3 raised then to an 8x minus 12. That equals, over here, power to power, we've got 3 raised to 3 distributed to 7 minus x, be 21 minus 3x. And at this stage in the game, I'm going to use the laws of common sense, where if these two sides are equal and these two bases are equal, then the exponents, they must be equal, right? So 8x minus 12 must equal 21 minus 3x. Now solve for x. If I add 3x over here, I've got 11x. If I add 12 over here, I've got 33. Divide by 11, and x is 3.